Hey guys, so today I would like to do a discovery with you. I'd like to show you using the calculator, using technology, and you can follow with your calculators at home, how to verify the graphs of our quadratic functions. And let's also realize what happens when we tweak our function a little bit, when we add a few factors, when we remove them, when we change them. So that's basically it. So get your calculators and let's get it done. Now, today's lesson is going to bring you back a lot to the concepts of our transformation of functions, and we'll see that at the end. Let's start by thinking about a very simple quadratic function, and this is actually the simplest one, y equals x squared. And what I want us to analyze is, okay, what happens if I add something, a constant, to it? So let's get our calculator and let's go to graph. So it's menu 4. Here in this window, I'm going to talk about a lot about this because I'm assuming that you're not familiar with it, but you can skip some of the things I'm going to tell you if you know how to plot functions already in your calculator. So here we have y1, y2, y3. All of those here are possible functions that you can input in your calculator, and all of them may be plotted at the same time. So what I'll simply do here is type x squared. A few things for you to notice here is, first, I'm keeping the calculator to your right, the whole body of the calculator, so you can see exactly what I'm typing in or clicking at. And also to the left, you can see the screen in a larger size, so it's easier for you to see the graphs that we're going to plot afterwards. Okay, so that's our first function. One thing to know here is that all of those buttons that I have here, F1, F2, F3, they will do those functions that you see up here. So if we press F1, we can select or unselect this function, and it will be plotted if it's selected, or it will not be plotted if it's not selected. So it's good to know about this because you can actually input a lot of different functions that you want to analyze and plot them as you want them. So for example, I've added three functions here: x squared plus 2, and x squared minus 2. Now all of them are selected, so if I draw them, if I plot them, they will all be plotted and I won't really, perhaps I won't know which is which. So first, I will just plot the first one. So I have unselected the bottom two, and now we could just press our draw button, F6. So there you go. That's what we would expect of a graph of a quadratic function. One thing to note is that it's concave upwards, and we should remember that, right? That it's concave upwards because x squared here is positive. So a is 1. Let's go back to our function. If we press F6 again, we go back to the previous screen with our equations, and we can see here this is simply x squared, and x here is positive. If we plot negative x squared, we can see that it would be concave downwards, and we can see that both of them were plotted at the same time simply because both are selected. If we go back and unselect the fourth one and draw again, we can see that it's our graph again. Now, let's say that we want to, I don't know, just browse through this function, so trace through it, try to analyze some points, try to realize how x changes, as y changes. So we can press here F1, trace, and it's going to bring us a cursor. And by pressing here, either left or right, we can browse through the points. So we can see here, for example, x equals 1, y equals 1, and that's expected because 1 squared is 1. So we would expect, for example, for x equals 2, y would be equal to 4, since 2 squared is 4. So if we keep going to the right, we'll find x equals 2, y equals 4. So that's quite useful. Let's go back now, and let's now see what happens if we add a value to our quadratic. So let's select this function, and let's draw it. Wow, look, it seems to be shifted upwards, and it also matches what we learned back in transformation geometry, that we would expect our function to shift. Now, you can browse through your drawing, through your graphs, by pressing on this cursor here. So you can take a look, for example, how those two approach up here. You can see that they never actually touch. Also, you can trace here as well. So you could analyze some points up here. Oh, look, 4, y equals 16. That's expected because 4 squared, or negative 4 squared, is 16. So that's something that you might use to understand a bit better your functions and to be able to analyze how they are. Okay, so let's now select the first and the third one. Just for you to remember, this third function is x squared minus 2. So we would expect this to be the same as the first one, but shifted downwards by 2 units. Let's see. Draw. And now we need to scroll downwards back to our origin, and there we go. Unfortunately, this calculator here is black and white, so it's not that easy for us to distinguish between those two functions. Some of the newer models, they're colored, so you can easily distinguish between them because each equation will be in a different color and each graph will also be in a different color. However, you can easily just unselect the first function here and draw it again, and you'll see that it's shifted downwards. We can trace it, and there you go, x equals 0, y equals take away 2. Whereas for the first one, if we trace, x equals 0, y equals 0, so it was shifted, it was translated downwards by 2 units. So from this, we can get to a more general idea that if we change our original function by a factor of k, we're going to shift it upwards by k units. And if this was a negative sign, we would be shifting it downwards. Right? And that also matches what we learned in our transformation geometry. Alright, so let's go to the second part of our investigation. And now, let's discuss what happens when we tweak with the x here. So if we add or subtract something to x inside of the bracket here. Just for some purpose that we'll see in a few minutes, instead of putting a positive sign, I will instead put a negative sign, and we'll see. For those of you who remember our transformation geometry, you will instantaneously realize. Just to have one example, let's tweak with 2 again. So let's try x minus 2 squared, and let's see what happens. So let's go back to our calculator here, and well, let's delete this. So we can press here F2, it's delete, and then F1, F2, F1. So this is our fixed function, our simplest one. It could even be considered our control in science, and that's the base for our comparison. So the first function that we're gonna add here, I will open bracket x minus 2 close bracket squared. You have probably noticed that the squared here is done by using a um, like tilde here, a hat, and this symbol is actually called caret. All right, and it's used to design or to specify powers. So that's the first function we are going to compare it to. And yeah, let's draw it. Wow, so it seems to be shifted. And if we had to do a polite guess, we would assume that it's 2 units, just because, well, that 2 has to be here somewhere. But we can do something better. We can go back. We may turn the first function off, draw it again, go to trace, and look for our 0. And our x is 2 when y equals 0. So our function was shifted 2 units to the right when we subtracted 2 inside of the brackets here. So it's another translation. And this time, instead of shifting up or down, we are shifting it sideways. Notice that if I go to the left here, 1, 1, 0, 4, the shape of our function has not changed. It's still the same curvature. However, it's just shifted. It has just been translated. It has not been warped or stretched in any direction. That's really important to notice. Now, knowing this, and if we are right, what would we expect to happen if we add 2 instead of subtract? Well, we would expect this to shift to the other direction. And let's see. So using technology, this is quite easy. But remember that you can always use the previous ways that we have learned to solve this if you don't have technology available. So let's draw this. There you go. Again, we see both functions, and if we want to analyze only just one of them, we can turn this one off and we can trace just that one. X equals 0, y equals 4. We can see that it's also not stretched. 1 will be 1 and negative 2 will be 0. So that's the second part of this investigation. So what now if we combine those two methods? So not only subtracting something, but also adding something else. So let's say I'm subtracting k and adding c. We could devise some polite guesses about this, because we already know what happens when we add something inside of the brackets or subtract something inside of the brackets. And we also know what happens when we add something outside of the square. So our polite guess is that it would be shifted up or down and left or right depending on those two values. So looking at the graphs that we have dealt before, that we have seen before, this unit here, if we subtract k, it shifts left or right. And adding something outside will shift it up or down. So k in this case here would mean how much have we shifted to the right, right, if this is negative. So if it was 5, my function would be shifted 5 to the right, and c, it would be shifted c up. And let's see. So now we don't quite need any of those functions because we already know how this works. We don't need to show this every time. And let's plot what matters. Let's plot simply something like this, which we know how works. So x minus 2 squared is a function which is shifted to the right by 2 units, and it has not been warped in any way, has not been tweaked in its curvature. It's still the same quadratic, the same parabola, just shifted. Now let's analyze now if we have exactly the same thing, but we add another factor. And here you might ask, why 3? Well, just because if we put 2 and 2, it's not that easy to analyze if which 2 isn't, it's changing what. So if we have different numbers, we may see what shifts left or right and what shifts up or down. So there we go. Let's draw those, and well, we can see that our function was shifted to the right by 2, and adding 3 shifted it up by 3, right? So if we had here simply x squared and we drew both of them, we can see that it's basically shifting to the right by k units and up by c units. So in a more general way, let's say this is our quadratic, and this could be just simply y equals x squared. And if we add, if we have a function which is x, let's say minus 2 plus 3 here squared, we are shifting this to 3 units right, 2 units right, 3 units up, and that's where our new graph would be. And again, it has not been warped in any way, it has not been stretched, it has just been shifted. And the numbers here that show up, this 2 is 2 here to the right, and this positive 3 is 3 up. If you remember your transformation geometry, this could be considered your object P. This is your image, right? So P dash. And this is your translation vector, right? So your translation vector HK, in this case, would be KC. But if you rewrite that in the form y equals x minus h squared plus k. And interestingly enough, h and k will be the coordinates of the vertex of your parabola, which is this point here, the bottom point, or if it's concave downwards, it would be the topmost point. Now lastly, let's analyze what happens if I multiply my x squared by something. I've added, I have subtracted the square and outside the square, so that's, I think, basically what else we can do. So what happens if we multiply this? So let's try a few functions. Let's try simply x squared, and let's compare to 2x squared. And also, if we feel like we need to, let's compare to half x squared, and let's see what changes. So let's open our calculator again, graph, and let's delete those two functions. Oh, well, let's keep this one, and let's now write 2. Sometimes for some calculators you have to type multiply For some you don't have to. I'll just put this one just to make sure. So 2x squared, and let's draw them. So the vertex is at the same position, which matches what I just told you and what we realized from the results from the third part, the last one that we just saw, when we translated our function by h and k. But in this case here, it doesn't move, it just warps. It's stretched, right? And how stretched is it? And let's see. So we know that our function x squared has some points which are quite well known to us. So we know, for example, that when x is 1, y will be 1. When x is 2, y will be 4. So what we could do here is check where are those points in our second function. So if we draw it and trace it, first let's go back to 0. 0, 0 is a common point in both functions. What if I go to x equals 1? In my original function, x equals 1 would provide me y equals 1, but in this case it's giving me y equals 2. Let's go forward. X equals 2, y equals 8. So yeah, all of the points, they are twice as high as they used to be. So my function has been stretched. Now what if I had, instead of 2, if I divided by 2? So let's try it. So 0.5, or you could just type a half, multiplied by x squared. And yeah, let's plot the first one and the third one. It's also stretched, but in this case it seems to be stretched outwards. And if we trace this function, we'll see that yeah, it's basically the one before, but half the height. If we keep going to the right here, x equals 4, the other one, y equals 4, the other one would be y equals 2, and that's it. Next point, for example, y equals 4.5, the other one is 9. So this function has been also stretched, but all of the points have got closer to the x-axis, not away from it. Whereas when we multiplied by a number which was larger than 1, then all points were stretched upwards. Now, this is also the case that it would be quite interesting for us to analyze what happens if we multiply by a negative number. So what if we just do negative x squared, and we know what happens, but we can see on real time here, and we can have a different perspective on this phenomenon now. We can see that it's actually a function which was so stretched downwards that it's its own reflection. The result is, yes, indeed, the reflection of the original function. But what generates this reflection is the actual stretching in the negative direction of the y, and creates this perfect image which is equidistant to the y-axis in every single point, however in the opposite direction, the negative way. And now the last thing that we can do here is actually combining all those crazy things that we have been doing so far. So what if I not only multiply, but I add, well, subtract something here inside of the brackets and add another thing outside? Wow, that's some crazy transformation. Let's see how this goes. So, going back to our calculator, going to graph, and now let's delete all of those functions down here, and let's plot the function that we want. Now let's try just multiplying by 2, subtracting h equals 3 and k equals 4. So y equals 2, h equals 3, and k equals 4. Alright, so our function will then be 2 times open brackets, x minus 3 squared, plus 4. Let's draw them, and let's scroll to find it. So we can see that it was shifted to the right, and it was also shifted upwards, and that's what we would expect since h is positive and k is also indeed positive. Now a is positive, so we would expect this curvature, to be thinner, right? It's stretched in such a way that um, it all points are higher, right? So it has been stretched in the y direction. So let's analyze what is our translation vector. So let's trace this function. So where would be the vertex of this one? So take a look, the vertex is at 3 and 4. So that's our invariant point. That's the point that has not changed. It's still the vertex. And look at those. H is 3, K is 4. So those are the coordinates of our translation vector. It's still those same points. And all the rest of the function is the same function that we had when we multiplied to x squared. So it's the same stretched function, however, shifted 3 units to the right and 4 units up. Now, just because I have a hard time believing in things the first time, I'm going to try some different numbers here. So now I'm going to try and stretch my function in some other way. I'll try h equals 1 and k equals to 3. So let's go back to a calculator and let's go back to the functions here. Let's delete this one, I don't need it anymore, and I'm going to type in the new function. So 0.5 multiplying open bracket x minus 1 squared plus 3. Remember that the negative inside of the bracket is going to shift your function right. Okay, that's very important, and it's a very common mistake. So enter, draw, and there we go. Let's trace. So if we trace the transformed function, that's exactly what we predicted. 1 to the right, 3 units up, and we can clearly see that it's our function just stretched in a way that all points have gotten closer to our x-axis. Now, just one last thing. Let's put some negative numbers in here. So let's try a equals negative 1, h equals negative 2, and k equals negative 1. So what would we expect to happen to this function? Well, a is negative 1, so it should be the same shape but shifted downwards. Well, actually warped downwards. It's going to be concave downwards instead of upwards. H is negative 2, so we would expect it to be shifted to the left by 2 units. And k is negative 1, so we would expect this to be shifted downwards by 1 unit. So let's see. Let's delete this function here, and let's add our new function. So this is negative x, open bracket, x plus 2, close brackets, squared, minus 1, right? So a here is negative 1, k h is take away 2, so it becomes positive 2 inside of the bracket, and negative 1 here is simply negative 1. So let's plot this function. Oops, enter, plot, draw, and there you go. Well, it seems to be shifted downwards. That's what we expected. Seems to be the same curvature. What we can do to analyze this curvature, we can go a bit further away from our function. So I'm going to set a new x min, and no, let's just warp y directions. So we have here y min and max. So we can set this, for example, to negative 10 and positive 10. And then we can draw the function again. And there you go. The curvatures seem similar. We can trace the function and try to find the point. So vertex originally was 0, 0. If we go to our new function, our new vertex is 2 and negative 1. Negative 2 and negative 1, which is exactly what we predicted. Negative 2 because of h, negative 1 because of k. And the negative 1, a equals negative 1 just made our function concave downwards, but it's still the same curvature because it's 1. If it was some number which was less than 1, and I mean negative less than 1, so absolute values less than 1, it would be a function which is smoother. It would not be as steep. The more you increase your a, the steeper your parabola becomes. So that's a good way of viewing it as well. And I believe that all those different functions have probably given you a quite good understanding of how those graphs are and how do they shift. And also it's a very good recap on some of our transformation geometry.